When a storm hits a reservoir, water level can rise fast, and predicting how that flood wave moves through the system is critical for dam safety, flood mitigation, and emergency planning. This process is called reservoir routing, and it helps us understand how inflows transform into outflows, how storage responds, and ultimately how a reservoir behaves during extreme events. Today we step into the most widely used tool for reservoir routing, known as level pool routing. In just a few minutes, you will learn how it works and why it's so powerful. Then we will walk through a step-by-step numerical example to put theory into practice. Let's get started. When a flood wave enters a reservoir, the water level starts to increase. In general, storage in the reservoir is a function of water level. On the other hand, the outflow from the reservoir also depends on the water level. This outflow could be controlled through assets such as pipes or gated weirs, or uncontrolled through spillways. Since both the storage and outflow are functions of water level h, we can conclude that the storage and outflow are associated, which can be shown as S equal to F of Q. This storage function can be variable or invariable. The level pool routing method, also known as the modified Puls method, works with an invariable storage function. This type of storage function works with the following four assumptions. First, the water surface in the reservoir is assumed to be horizontal. Second, the reservoir pool is assumed to be wide and deep compared with its length in the inflow direction. Third, the flow velocity within the reservoir is assumed to be very small. Finally, for a given water level, outflow discharge is assumed to be fixed. To derive the level pool routing formulation, we start with the continuity equation. The changes of the storage over time, ds over dt, is equal to inflow minus outflow. Similar to channel routing, the inflow hydrograph is expected to attenuate and translate after going through a reservoir routing. If we want to look for the maximum storage during this process, we need to solve ds over dt equal to 0. Referring to our continuity equation, we will get 0 equal to I minus Q, or inflow is equal to outflow. This means the storage reaches its maximum at the point where the inflow and outflow intersect, what we call the point of inflection. On the other hand, Q is also a function of h. For example, flow over a weir can be calculated using this equation, where CD is the discharge coefficient, L is the weir length, and capital H is the head of water on top of the weir crest. If the reservoir water level H increases, the capital H and consequently Q will also increase. Therefore, it is fair to say that the maximum outflow occurs at maximum H or at maximum storage. This means the peak of routed outflow in the level pool routing method always falls on the recessing limb of the inflow hydrograph. Note that in this diagram, the shaded area in the rising limb represents the buildup storage in the reservoir, while the shaded area in the recessing limb represents the depletion of storage in the reservoir. Now let's get back to our continuity equation and rewrite it in a discrete form. In a reservoir routing problem, inflow is known. On the other hand, we generally know the initial values of storage and outflow. That means for the first time step, the continuity equation has two unknown values of St and Qt. Let's bring all unknown variables to one side of the equation. Now, let's multiply both sides of this equation by 2. To find two unknown variables, we need another equation. For this, we will bring in the storage outflow function. This relationship could be available as a formula like this, where k and n are constants which can be found through a curve fitting analysis. However, in practical applications, we usually have a dataset of storage versus outflow records. In both cases, we need to establish a relationship between the unknown term of 2s over delta t plus q in the continuity equation and the outflow q. With these, in each time step, we calculate the right side of the equation, which is known, to get 2s over delta t plus q value. We then refer to our established function and find the corresponding q. Having that, we can find the corresponding storage. This process can then be repeated for all remaining time steps. Now, let's solve a numerical example to better understand this process. The inflow hydrograph data into reservoir is given as shown. The record of storage outflow data is also provided. The initial storage is assumed to be 5.43 million cubic meter. We are supposed to use the level pool routing method to calculate the outflow hydrograph and its peak, estimate the reservoir lag, and finally estimate the maximum storage. Note that our delta T in this example is 3 hours or 10,800 seconds. In the first step, we need to establish a relationship between 2s over delta T plus Q and Q. For this, we use the given S and Q data to calculate 2s over delta T plus Q. Be mindful of the required unit conversion. For example, for the first S value of 5.3 million cubic meter and a discharge of 0, our desired term will be 2 times 5.3 times 10 power 6 divided by delta T of 10,800 plus Q of 0. That will give us 981.48 cubic meter per second. We need to repeat this for all values. Then we plot 2s over delta T plus Q and Q, where 2s over delta T plus Q is on the x-axis and Q is on the y-axis. We then fit a line and find the equation. In the second step, we set up the tabulated calculations. The first 2 columns will be allocated to the inflow hydrograph data, time and inflow. The next 2 columns are for the right side of the continuity equation. First, IT plus IT minus 1, and second, 2s over delta T minus Q. Then comes our left side of the equation, 2s over delta T plus Q. Finally, the last column will be for our desired output, the outflow Q. In the third step, we initialize the table. Having initial storage of 5.43 million cubic meter, we refer to the provided storage outflow data to get our initial outflow Q0, which will be 8 cubic meter per second. This sits in column F. Remember that we have already calculated the 2s over delta T plus Q for the given table, including these initial values of S and Q, which sits in column E. Then we can calculate 2s over delta T minus Q by deducting 2 times Q from 2s over delta T plus Q. That will give us 1013.56 minus 2 times 8, which will be 997.56 cubic meter per second. In the last step, we start the iterative process. First, column C, the summation of inflow at current and previous time steps, 10 plus 21, which give us 31 cubic meter per second. Then we use the continuity equation to sum the terms on the right hand side to obtain the unknown term on the left hand side. 31 plus 997.56 will give us 1028.56 cubic meter per second, which sits in column E. Now, we refer to the established relationship between 2s over delta T plus Q and Q to get the corresponding outflow value. This gives us 8.75 cubic meter per second. Finally, we use values in column E and F to find the value of column D. 1028.56 minus 2 times 8.75 give us 1011.05 cubic meter per second. Let's do one more row. First, the 2 inflows, 21 plus 38, will give us 59 cubic meter per second. We add 59 to the previous 2s over delta T minus Q of 1011.05, which gives us 1070.05 cubic meter per second. We then refer to the storage function to get the corresponding Q. This gives us 17.77 cubic meter per second. Finally, we find the value of column D. 1070.05 minus 2 times 17.77, which give us 1034.51 cubic meter per second. Now that we have built the framework for this analysis, let's take it into Excel and work through the calculations. So now we are ready to continue the calculation in Excel. The first step, which was the establishment of a relationship between 2s over delta T plus Q and Q, was already shown. So this is the same diagram and the same calculation in the table. So now I'm going to use that, but I'm going to reiterate the process of finding the first 2 rows and then dragging and copying all those values using Excel. So what we did was the initial value of Q is going to be adopted from the given storage that we had. So it is going to be 8. It's a known value, so I give it a blue color to tell that it is an initial value, so it's not calculated. Similarly, the 2s over delta T plus Q was also based on the initial value of storage and Q, so practically I'm adopting the calculation from this table. I'm just using it. And then our 2s over delta T minus Q will be simply calculated by the 2 values that I just found, which will be the value of this column minus 2 times the value of Q. And that will be my answer. So now we are ready to start. So this was only the initialization of the process. So I start from this row. So my first cell is going to be the summation of the current flow plus the previous inflow. So that will be this one. Then as we discussed, we jump to 2s over delta t plus Q value, which is going to be equal to this value of inflow plus the previous value of 2s over delta t minus Q. And that will give me this. After that, this is the critical point. We need to enter the formula that we found in this curve fitting. So in order to find Q, I'm going to use this equation. So I say that it is 0.2172 multiplied to the value of 2s over delta t plus Q minus 214.65, and that will give me the calculated Q. Having that, I come back to this column, and similar to the previous one, what I'm going to do is the 2s over delta t plus Q minus 2 times of the current Q that we found. And that will give me the number that I want. After that, we just need to select these cells and copy them all the way down. I've already built in the outflow values in the same diagram. So you see the blue one is the inflow hydrograph, and then the orange one is the outflow hydrograph. Again, the translation and attenuation can be seen. If we look at the peak values, in the inflow, the peak value was 82 cubic meter per second, while the peak in the outflow is 64. So you see that there is a big drop, and that's attenuation. Then there is a lag also. So the peak in the inflow happened at 12 hours, but for the outflow, it happens at 18 hours. So there is a 6 hours time difference. That's exactly what we call the reservoir basically delay or lag. To find the maximum storage, we need to find the maximum outflow discharge and then bring it into this curve fitted function that we found in order to find the corresponding S value, which will be the maximum S. The problem that we have here is that because of relatively a large delta T that we have, we are basically missing the actual peak on the orange diagram somewhere between these two data points. So basically our real peak happens like this somewhere in between, but it is fine. We can roughly estimate the value of that based on the numbers that we have. This actual peak should be slightly larger than 64. Let's assume it as 65. So I assume that our Q peak is equal to 65. As you saw, our fitted function was like this. So now we have our Q peak of 65 cubic meter per second. If we put our Q peak that we just found, we can solve this equation and find the only unknown variable, which is S. So the value that we find is 6.6 million cubic meter. This S is going to be the maximum storage because it is corresponding to the maximum outflow discharge. That was level pool routing, one of the most practical and widely used tools for reservoir flood analysis. In the next video, we will take this a step further. We will explore how routing is implemented in major hydrological models such as HMS, RORB, and SWMM, comparing their routing method, the key required parameters and assumptions to see how they handle real-world catchments. Stay tuned.